Okay, I'm going to start with drawing the structure of membrane, commonly known as selective membrane. Because of its selectiveness, obviously, it doesn't just allow any molecules pass through. It's especially big molecules and ions. Not that ions are big, but they have charge and they need a special channel to get pass through the selective membrane. And the structure looks like, in general, something like this. And because it's bilayer, but this is very generalized or sandwich structure. In general, it looks like something like the head, or which is hydrophilic or water attractive layer, and this part is hydrophobic layer, or something that's like soluble by water. So this is most commonly known as sandwich structure, and this is how it looks like, the selective membrane looks like. But the thing is, it needs a special channel for the ions or small ions to get passed through it, that are very important for our cell to survive. So something like this. These are the channels that we have. And now that we are talking about potential of sodium and potassium, those two are one of very important ions for our survival. And something like this for protein channels, or like big molecule channels. And this is, let's say, inside of the cell, and let's say this part is outside of the cell, then this is, in general, is plasma membrane or selective membrane. So what we're gonna do is that this difference in potential can create a force, which is K common and KQ1, Q2. Those are the charges from sodium and potassium, and the distance between them. Now that we have very small distance, it can create large potential differences. And let's say here we have higher number of potassium and lower number of sodium. Sodium is low. So how does this create the force that we need? At rest, or like what we are talking about is the at rest. So at rest, inside of neuron is more negative than the outside, because of the potential that, or the charge that diffuses out of the cell because of potassium and sodium. And this happens to ions movement, and the sodium potassium pump actively pushes three sodium outside of the cell here, then latest 2 potassium inside, so 2 potassium. So this makes a lot of difference when we talk about making inside loss more positive charge. Then positive potassium leaks out through open channels more than sodium leaks in, keeping things negative inside. Large negatively charged protein inside the neurons also help maintain the charge balance. So how do we get the negative 17 millivolt that we need for our cells? So it is the balance point where the first drive potassium out and pulling sodium in, reach in equilibrium, the negative 70 millivolt. Any charge from this baseline gets the neuron ready to fire or stay quiet. So this one, the 70 millivolt that we are talking about, is a balance line. Then ensure that the neuron stays at negative 70 millivolt, that is potential difference because of ion pumps, leaky channels, and charged proteins. This sets the state of action potentials, allowing neurons to communicate efficiently. That's all about what I learned from the video. Thank you.